Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise VTU paper tutorial of electrical circuit analysis of December 2016. In this tutorial, the questions of module 1 are solved. I prefer to explain the concepts involved and illustrate the thinking process before you start solving any question rather than the detailed mathematical steps. I feel you are well equipped with basic mathematical skills required to solve the simultaneous equations. After going through this tutorial, I am sure you will earn some skills involved which will help enhance your confidence. Friends, to be comfortable and to be able to grasp the contents of this module 1 tutorial faster, I feel you should be well equipped with 1. To identify the connectivity of the given network and to write the mesh and nodal equations correctly and solve them. So, I suggest you go through some of my earlier tutorials listed in the table. Friends, first let us solve the question on mesh current analysis. In this question, we are required to find the unknown mesh currents. Observe the given network. All three mesh currents I1, I2 and I3 are already identified. Also note that I1 is equal to 15 amperes, so we know. Hence, the solution is simple. We need to obtain another two balance equations. But observe that there is a voltage controlled current source in one branch. So, one branch equation should necessarily be written for this branch current. By writing the balance equation for the branch, we get I3 minus I1 is equal to Vx divided by 9. By substituting I1 is equal to 15 amperes, we get equation 1. But what is Vx? You find that Vx is the voltage drop across 3 ohm resistance and current through 3 ohm resistance is I3 minus I2 amperes. Why I3 minus I2? You see that the polarity of voltage across 3 ohm is positive on the left hand side and negative on the right hand side. So, the true current in 3 ohm resistance will flow from left to right. Therefore, Vx is equal to 3 into I3 minus I2, let it be equation 2. By equating the right hand sides of both equation 1 and 2, we get 9 into bracket I3 minus 15 is equal to 3 into bracket I3 minus I2. By solving it, we get I2 plus 2I3 is equal to 45. Let it be equation 3. We need one more balance equation. Hence, writing the balance equation for loop 2, we get minus I1 plus 6I2 minus 3I3 is equal to 0. By substituting I1 is equal to 15 amperes, we get 2I2 minus I3 is equal to 5. Let it be equation 4. By solving equation 3 and 4, we get I2 is equal to 11 amperes and I3 is equal to 17 amperes. And we know I1 is equal to 15 amperes. Friends, I will tell you how you should check whether your solution is correct or not quickly. First thing you should know that all the answers we have obtained are positive, so our assumed directions of all the mesh currents are correct. Then current in 3 ohm resistance is I3 minus I2 and hence we get 17 minus 11 equal to 6 amperes. Voltage across 3 ohm resistance is 6 into 3 equal to 18 volts. And dependent voltage source current is equal to Vx by 9 and that is equal to 18 by 9 which will give us 2 amperes. So, if you apply Kirchhoff's current law to this junction, you find that 17 ampere is entering the junction and 15 ampere and 2 amperes are leaving the junction. Hence, the Kirchhoff's current law is verified. Hope you are happy. Friends, now we shall solve the question on source transformation. In this question, we are required to find Vx using source transformation. If you observe the network, there are two sources which could be convertible. One, a practical voltage source of 6 volts in series with 2 ohm, and 2, a voltage controlled current source of 0.25 Vx amperes in parallel with 4 ohm. Vx is the voltage drop across 2 ohm resistance. So, out of the two convertible sources, which to convert first? In my opinion, first, by converting the dependent current source, we get a dependent voltage source of Vx in series with 4 ohm. Observe the polarity of converted dependent voltage source. Positive is on the left hand side because the orientation of 0.25 Ix amperes is from right to left. So, the converted voltage source also should drive the current from right to left. That is how you have to fix the polarity of the converted voltage source. Now, shall we convert a 6 volt source? You should know that even after converting, further reduction is not possible. So, let us leave 6 volt source as it is. Also, observe that the reduced network is a simple two junction network and there is only one unknown node voltage, that is Vx. Therefore, by writing the nodal equation for the node Vx, we get Vx minus 6 divided by 2 plus Vx by 2 plus Vx minus 18 divided by 4 is equal to 0. By solving it, we get Vx is equal to 7.5 volts. Friends, is it not simple? Next, we shall solve the question on star delta conversion. In this question, we are required to find the equivalent resistance between the terminals A and B. If you observe the network, two delta networks are easily seen. One is of 30 ohm, 10 ohm and 10 ohm which are in delta, and the other of 10 ohm, 2 ohm and 3 ohm which are in delta. We can convert any one of these two. So, I prefer to convert the delta of 30 ohm, 10 ohm and 10 ohm into star network as shown. We know that R1 is equal to the ratio of the product of two resistors connected to R1 branch divided by sum of all the three resistances. Hence, we get R1 is equal to 30 into 10 divided by 30 plus 10 plus 10, that is equal to 50, and hence we get R1 is equal to 6 ohm. Similarly, R2 is equal to 10 into 10 divided by 50, which we get R2 is equal to 2 ohm. And similarly, R3 is equal to 30 into 10 by 50, which we get R3 is equal to 6 ohm. By incorporating this converted star resistors in place of delta, we get the circuit shown in figure 2. Now, you can easily visualize that 6 ohm and 2 ohm are in series and their equivalent is 8 ohm as shown in figure 3. Similarly, 2 ohm and 3 ohm are in series and their equivalent is 5 ohm as shown. Now, if you observe figure 3, 8 ohm and 5 ohm are in parallel and their equivalent is 3.076 ohm as shown in figure 4. Now, 6 ohm and 3.076 ohm are in series and their equivalent is 9.076 ohm as shown in figure 5. So, from figure 5, we find that 9 ohm and 9.076 ohm are in parallel and hence we get RAB is equal to 4.518 ohm. Friends, this is how you should go on reducing the network, keeping the terminals across which you want to find the equivalent resistance without disturbing them. Friends, Next, we shall solve the question on nodal analysis. In this question, we are required to find the three node voltages V1, V2 and V3. Observe the given network. You find that there is one ideal voltage source of 25 volts in one branch and an ideal current controlled voltage source of 5I volts in the other. So, two balance equations for these two branches in terms of unknown node voltages should necessarily be written. Therefore, by writing the balance equation for branch V1 to V2, we get V1 minus 25 minus V2 is equal to 0. By rearranging it, we get equation 1. Similarly, by writing the balance equation for branch V2 to V3, we get V2 plus 5I minus V3 is equal to 0. But I is equal to V1 by 2. So, by substituting for I and solving, we get 5V1 plus 2V2 minus 2V3 is equal to 0. Let it be equation 2. We need another balance equation. So, let us write another balance equation for the reference node. Note that. So, by writing the balance equation for the reference node, we get V1 by 2 plus V2 by 4 plus V3 by 3 is equal to 0. By solving it, we get 6V1 plus 3V2 plus 4V3 is equal to 0. Let it be equation 3. By solving the three simultaneous equations 1, 2 and 3, we get V1 is equal to 7.6 volts, V2 is equal to minus 17.4 volts and V3 is equal to 1.63 volts. Friends, finally, let us solve the question on resonance circuits. In this problem, we are required to find C omega naught and half hour frequencies omega 2 and omega 1 given R is equal to 4 ohm, L is equal to 25 millihenries and Q is equal to 50. Especially, it is not given that you have to find frequencies in hertz. So, you can find omega naught, omega 2 and omega 1 in radians per second, and if you need frequencies in hertz, use omega is equal to 2 pi f and find the respective frequencies in hertz. Friends, there is no much thinking process required to solve this problem, but you have to remember and recall the relevant formulae to find the unknown based on the given data. In terms of R, L and Q, you know two formulae. One, Q is equal to omega naught L by R and 2, omega naught square is equal to 1 by LC. So, first using Q is equal to omega naught L by R, we can find omega naught. Hence, omega naught is equal to Q into R by L. Substituting the values, we get omega naught is equal to 8000 radians per second. Then, using omega naught square is equal to 1 by LC, we can find C. So, C is equal to 1 divided by omega naught squared into L, and substituting the values, you get C is equal to 0.625 microfarads. To find omega 2 and omega 1, first let us find the bandwidth. We know bandwidth is equal to omega naught by Q and that is equal to 8000 divided by 50, which will give us 160 radians per second. And we know omega 2 is equal to R by 2L plus square root of R by 2L whole square plus 1 by LC. Substituting the values, we get omega 2 is equal to 8080 radians per second. Hence, omega 1 is equal to omega 2 minus bandwidth. Substituting the values, we get omega 1 is equal to 7920 radians per second. Friends, thank you for watching this video.